asl375 students stay, rest of us. So have you guys seen the textbook yet? The one I'm going to teach? In most parts, not all. Not yet? I got it along. So you can pass it around and you'd see how most of the images, whatever I'm explaining, it's very nicely and simply written. Okay? There's a PDF that I have. I can pass it on to one of you and you can circulate in the class. But right now we are doing chapter 1 and 2, looking into the basic climate components, and there are a lot of other things in the book which have not gone into detail, but most of it is covered. So I mean, if there is any question when you read you don't understand, please feel free to ask. Okay? Yeah.
Could you send the PDF to me?
One of you, I'll send it to one of you, you can calculate. Okay? You write to me on my email address. Okay, I'll do. And is there a group
Yeah,
where you can, yeah, so just forward it. Okay. So last class we were looking at how differential heating of Earth takes place. Depending on where you are, it heats up differently, equator, poles, right? And we also have the seasons because of the tilt. And then we thought that if this is the case, and if equator is the so equator is heated the most, and as compared to the poles, so you have this difference in temperatures. Difference in temperatures causes air to warm up, warm air become less dense, rises, less weight of air, lower pressures at equator, relatively higher pressures on poles. And then there are other pressure differences also. Air rising would sink somewhere, rising air from the equator sink on the tropics, and on surface. So this is air rising, sinking on the tropic, and on surface, because this is a low pressure and this sinking air is very dry, a very sort of an adiabatic process. To fill up this low pressure, there is also winds going in from the high pressure to low pressure, and you see the winds are not going straight. There is Coriolis force which is acting. Now, I mean, I'm not, like I said, I'm not delving into the angles and explanation that I teach in the other class, but this is the book. You'll find it all here, why there's a deflection of winds that are moving from higher pressure to lower pressure. Simply put, you can imagine that Earth is rotating from west to east or east to west. Huh? Where is west? West is here, right? So always remember as V, W, P. Okay? So west to east, right? So in the northern hemisphere, it deflects to the right. So there is winds coming from high pressures to low pressure. They're deflecting to the right. Southern hemisphere deflecting to the left. All the explanation, please go through it. I'm not going to teach this. This is not directly relevant, but important for you to understand that why do winds deflect. Those of you who attended monsoon lecture might know, but definitely look at this book. Okay. So you can also imagine, for example, if there's a low pressure center somewhere, and there's winds coming from all the directions, and if this is happening in the northern hemisphere, would the wind move clockwise or anti-clockwise? You see what I mean? No? See, that's the problem with this class. There's just one. You have to move it up. Okay, so let's say there is a zone of low pressure. This is a zone of low pressure, and we are in the northern hemisphere. Okay, in the northern hemisphere, if you remember, winds were deflecting to the right because of the movement of the. Just learning for now, but go and read the book. You'll see why they're deflecting to the right. Coriolis force. Okay, so this is low pressures. You also have high pressures around it. Technically winds would go like this. I'm asking whether this would be anti-clockwise, mean rotation of winds, or it would be clockwise in this case. This is northern hemisphere.
Clockwise.
Clockwise? Why do you think so? हाई से लो में जा रहा है. Northern hemisphere में reflects to the right.
Okay.
Huh?
Anti-clockwise.
Anti-clockwise. Anybody else? You see what I'm saying? So it would reflect to the right, it would reflect to its right, it would reflect to its right. So what is the movement of wind then? Right? So this is anti-clockwise. So you would see, definitely go and read this page at least. That's why I brought this book. It's very nicely explained and written. Okay. We would talk a little bit about this when we talk about past climate states. So it's important. Okay. All right. So so what other thing distributes? What is the other circulation that distributes heat on the Earth's surface? We've talked about atmospheric. circulation. Winds are moving to distribute the heat, right? It's because of the unequal or differential heating of land and Earth's surface basically. That is what makes the winds to move. What other ways can we redistribute this heat and such that the equator is not the warmest and poles are not?
Water.
Water, right? So the next circulation that we'll talk about is the ocean circulation. So as you would imagine, water when it gets heated up, it's it's lighter. So solar radiation can penetrate up to 100 meters. What is the average depth of ocean? Do you think the solar radiation goes up to the bottom of the ocean? No, there's some abyss, right? So what is the average depth of? About, guess.
80,000. 6,000.
It's that, yeah, less than that. Average. There could be some trenches, about 4. So yes, ocean doesn't get the heat. Heat only penetrates until about 100 meters, and that's the surface ocean which gets heated up. Warm water becomes lighter, less dense, moves around. Okay, we've talked about this, but yeah, so moves around, and similarly, colder water would come. So there is this warm. Reds are all mostly going from the warmer regions to cooler regions, but there's also drift because of the winds. So winds also take surface water along them, and some of the tropical gyres are also made because of the movement of water, cold water coming towards warm, taking the space, and warm water being displaced and going to northern region. So these are some of the currents. Again, we're not discussing each of the current in terms of where which one goes, and you don't need to remember all this, but you should know that there is a great amount of surface ocean circulation which is because of the water being less dense, and also because of the winds driving them wherever they're going. Okay, so this is a process that so for example, in the northern hemisphere, if wind is going from warmer region to relatively cooler region, you would see, or low pressure zone from high pressure zone, you would see if it's northern hemisphere, surface ocean water would technically should follow this, but reflects to the right again because of the Coriolis force, and as you go in the deeper layer, this angle kind of changes and becomes what is called as the Ekman spiral. Not going into the depth, but these kind of movements you can also see, these spinning gyres you can also see in the ocean. Now, so these were all surface waters are moving around everywhere in the ocean, but do you know that ocean waters are also sinking? Like, what's happening with the bottom of the ocean? Is it not connected anywhere? Do you know that the water sinks also? The surface water? Yeah, it does sink, right? So the most of the sinking that happens is in the North Atlantic region. This is the Atlantic Ocean, North America, South America, Africa, Europe, Spain, India. So just to put you in context, this is North Atlantic. That's where Iceland, Greenland. Oh, by the way, the first class that I taught, one of your UG class, 2 years back, I asked where is Greenland? मेरी पहली class थी, and they said मैम बहुत grasses होती है यहाँ पर. So I was like, okay, कहाँ से start करूँ अब? So it was that bad. So I always and then in the second semester I started showing a map. Well, so लोग देख लेते हैं कहाँ पे क्या है. So Greenland has grow grass. So yeah, anyway, this is Greenland. Okay, lots of ice and snow, glaciers. So this is where the water sinks. Now the question is, why would the water sink?
Becomes
Lighter.
denser.
Denser. Why would it become dense? Temperature, yes, cooler water, dense. Anything else? So when ultimately when the water cools down, it becomes, what is it? Ice, right? Leaving behind, remember, this is salty water. Ocean is salty, leaving behind lots of salt. So even more denser. So there are two reasons for water to become. So that's why it's called the thermohaline circulation. Haline means salty, and thermo means temperature. The two reasons why the water would sink on those latitudes, northern latitudes. So by the time it reaches this region, there's plenty of water which is cooled down. There's also a lot of sea ice forming. Even here there is a lot of the circulation is such there's some actually downwelling or deep circulation happening around Antarctica, also not shown here. But this is the primary region where the deep water circulation starts. Okay. So average salinity, seawater salinity increases, temperature decreases, density. So all of these questions are answered. So deep ocean water, where does it come from? Mostly here, where the surface water is sinking. Okay.
Why is it not sinking at the other part? Like, I think that's rising here, right?
Yes. So we'll talk about upwelling in a bit. So it's also rising at other places. So we'll talk about upwelling and what is needed for upwelling too. Okay, that's a good question. So that is that. Here, there you go. So now we have the water sinking, so it has to come up somewhere. Otherwise, it will only sink and will swell up, right? So there is something called a process called upwelling. Okay, so upwelling again is because wind driven sometimes, so it's called the coastal upwelling. So near the coast, where wherever there is coast and where there is wind blowing parallel to the coast, it moves the wind along it, and depending on where you are, this is northern hemisphere scenario that they've shown. So you'd expect wind to surface water to travel with it like that, but then it sort of moves to the right because of Coriolis force. As it moves to the right, there is some space created. Bottom waters then come up and takes the space. So that's where this is what is known as the process of upwelling. Upwelling of water takes place most of the coastal regions where you have winds running parallel to the coast, and with surface waters are displaced, bottom waters coming up, bringing in lots of moisture, nutrition, nutrients from ultimately whatever is growing, phytoplanktons, they die and they decompose at the bottom. When the coastal upwelling happens, it brings in lots of nutrients on the surface. So for example, Peru, where this is a very typical in South America, American coast, very typical phenomena. You have lots of upwelling happening. Fisheries is their main sort of financial thing. So their economy depends on fisheries because of this process happening and this being very productive ocean. It can also happen around equator because when the winds are surface winds move, or warm surface water moves. Basically, trade winds going like that. Surface water again going deflecting to right on the northern hemisphere, and space created. So bottom water being upwelled on the equator regions. So two things are important: one, coastal upwelling, and one, equator upwelling in the case of bringing water back to the surface. So these are the two regions. Coastal upwelling occurs at a number of places. I don't think they've shown in the book, and also I've not put, but I'll bring a map probably next time if I can, and I'll show you regions or upwellings. Those are one of the most fertile regions in terms of productivity, ocean productivity on Earth. Okay?
In the case of coastal upwelling, shouldn't the wind move perpendicular to the coastal line because of the sea breeze and land breeze?
So that's a different phenomena. Like sea breeze and land breeze is differential heating of land
Yeah,
and
yeah.
sea, and depending on, and it's a diurnal. It happens in a day,
Yeah.
right? So during the day, land is heated
Yeah.
more, low pressure, high pressure, so winds rushing in. So that
Mhm.
happens. That is more of a day, night, and night.
Mhm.
Lands get cooled down.
Yeah.
There's low pressure here. Those are diurnal phenomena, and it is not major. These are long-term phenomena and permanent sort of phenomena. And what you're talking about, they are just the scale is different.
Okay.
Right. So yes, there is some wind, surface wind, which would, and the intensity is different.
Mhm.
But while these are long, if you talk about synoptic scale, mesoscale, these are different scales. Phenomena is occurring at different scale. These are winds which are basically trying to balance out long-term pressures, like equator is low pressure, tropics high pressure, poles highest pressure, those kind of things. This is more of a temporary phenomena, happens day and night. Depending on where you are. So again, this is a video that I put last time, and you can see how the deep water sinking near Greenland. This is called as the thermohaline circulation, and you can see the water is going in the deep ocean there. And the gray arrows that you see now is actually bottom water circulation. They are coming. They are now traveling southwards, and it upwells at various regions. Now, while this plays on, one question is: can we disturb this thermohaline circulation or sinking of water? How can it be? We're talking about, this course is about paleoclimate. We talk about climate change. We talk about how humans are, interfering with the climate, natural climate variability. Do you think we can change, or anything can be done to this thermohaline circulation? What do you think would be the future of this sinking, or we also call it Atlantic Meridional Overturning Circulation, AMOC. You would hear, if you do any other climate course, you might hear AMOC changes. Why would this overturning circulation change? There's another circulation that goes around Antarctica. I'm not talking about that, but that one there, around North Atlantic. Do you think so? Why would, yeah.
Probably near Greenland or something like that, if the temperatures are increasing,
Right.
then the sinking water, it shouldn't sink more.
It wouldn't sink,
Yeah.
or it will. It is in the right direction, but temperatures would not change so much. Like it would not become 25 degrees or 30
Probably,
degrees.
like the density changes because of adding temperature.
Adding what?
Like
Melting.
not so
Melting.
some oil spill or something.
Melting. Yes, there would be ice, whatever is there on the continental ice, that would melt. And what would happen then? So if you remember, thermohaline circulation was temperature and also haline, so salt water. So that water is really salty. If you look at the salinities there, they're above average salinities, right? They're not. That's not fresh water. 35 PSU, 38. Really high salinity, 39. Now, if there is melting of ice, ice is what? This water, fresh water, right? That fresh water, when it melts, it goes in the ocean, and technically it should be really salty for it to go, sink. But because of the fresh water, it would not sink. I mean, it won't collapse. The circulation would not collapse, but it slows down. Right, the amount of water that was sinking would not. The density changes. Right, so those fresh water, the fresh water addition that can happen in future would actually slow down, and it has happened in the past, by the way. Thermohaline circulation has slowed down in the past, and that slowing actually caused, like, monsoon changes, and whatever happens there has huge impact on what we are experiencing now. So Indian monsoon can change because of what is happening in the North Atlantic. It does not sink, it does not carry the heat, because it's ultimately carrying the heat, right? These water masses which are moving northwards and ultimately sinking, they're carrying the heat. If it does not sink, there's fresh water, the water which was kind of, taken to the,
What is the cycle time?
cycle time. Yes, that's a good question. It's about 1,000 years, and if you should look at the it can take, like, if the depending on the freshwater input that you put, it can be also on century scale.
So global warming is like a still recent phenomenon.
Yeah, so I'm talking about natural climate variability. But the rate we are putting in CO2, remember we are talking about 500,000 ppm. I mean, the temperatures would increase drastically. And in the natural, if you remember the first plot that I was showing, the naturally we had seen such CO2, but on millions of scales of time. So naturally it changes at thousands of years. But then, the way we are putting in CO2, we are changing it at very fast rate. So something that was occurring on century scale, you can see it, 10 years or 20 years, or, depending on how fast we put in CO2, how fast we warm the atmosphere, and how fast we melt the ice that is there.
Cycle time here means how much time a unit of water takes to complete a round trip.
Residence time of, any water in the, yeah. So also I think I did not dwell on the response time, which I showed it quickly, I think, on the first one of the first few lectures. But there is a in the first chapter you would see that there is a nice explanation of response time, and there they would talk about thermohaline. Anybody remembers? We talked about response time, or cycle time. Yeah. So I did not talk about this example of Bunsen burner, and how what all it's how the water in that Bunsen in the flask here warms, and what is the response time of this water to completely warm, and this they relate to various processes happening. I think I showed this table, if any of you remember. Yeah. So there you see that longer response time. So for deep ocean, it's about 100 to 1500 years. So response time is that if there is a natural anomaly, if suddenly some spot cycle increase or whatever, that impact for the entire the cycle that it would take, or that is about 100. So from century scale to 1500 years of time is when water mass is actually deep water and comes up wherever. So that is a scale. But with the way we are going on that linear scale where we are putting in CO2, it would be rather fast. Okay.
But if the water is not sinking, so shouldn't the response time increase, because it will not impact the depth of the ocean because it's not sinking?
Yeah, that's the problem, that it's not sinking much. So ultimately, what is this doing? This is taking the heat from the warmer regions northwards, right? So let's say let's take an example of India. So ultimately, the warm waters or whatever they're moving this way and they're sinking. Because the water is not sinking, this heat movement northwards is not being moved, right? So there is a heat buildup in these oceans, in the Southern Ocean, Indian Ocean. What this causes is, because if you remember, we were talking about the Hadley cell and how monsoon, surface wind go. There is low pressure because of Tibetan plateau. We'll talk about monsoon in one of the lectures also. But monsoon occurs because there is a pressure thermal gradient, right? Very hot summer and relatively cooler because of high specific heat. And now that relatively cooler waters are not so relatively cool. So the thermal contrast between water and land is decreased because there is a heat buildup here. So that would change hydrological cycles everywhere, not just in India, but since monsoon is India is primarily Indian subcontinent. This entire region has monsoon as one of the largest ocean atmospheric process going on, and our economy depends on that more or less. This thing is very important, but not just here, like Africa, all of these tropical belts and Australian Indonesian monsoon, everything would be impacted, because ultimately heat storage in this ocean is a completely different problem. Yeah. So then, the response time question will not even come, because it's not even, it won't upwell. It's just heat building up here. This has stopped completely, right?
So like the deep oceans won't be impacted by the temperature difference.
Yes. Yeah. Right. So there's also I've put in this. I don't think it's here in this chapter, but somewhere in the book I've put in these slides to show where we have ice or sea ice or continental ice or mountain glaciers. Oh, it's in chapter 2. So basically, sea ice, as you can see, the formation and melting of sea ice are driven mainly by seasonal changes in solar heating, such that Arctic sea ice, for example, so Arctic is the northern, sea ice. There's lots of sea ice in the North Pole around Arctic, right? So that sea ice, that's not permanent. It decreases depending on what time of the year you are there. So it kind of opens up a lot of transport routes. So if you want to go, like if let's say if China wants to send something to the west, usually it would go around the Arabian Sea, and Suez Canal, and that route. But it has opened up because of the warming. Sea ice that used to be permanent sea ice that used to be there, it is now melted. So it has opened up routes for it to go across, and so sea ice is not permanent. It's more it's seasonal. But now it's kind of even the permanent sea ice that is also starting to fade away because of the warming that we are facing. I think I've given this is Arctic example somewhere and might bring it up again. But so in the Southern Ocean, most of the sea ice melts and forms again every year over an area comparable in the size of the entire Antarctic continent it's around. This annual sea ice, again, you don't need to learn the numbers, what is the thickness, but these are just facts that you should know, and it just gives you a picture of what is there on Earth. This annual ice cover averages about 1 meter in thickness, except where strong winds cause the ice to buckle and pile up on the ridges. In contrast, the land masses around the Arctic Ocean constrain the movement of sea ice and allow it to persist for 4 to 5 years. So when they say that it is persisting for 2 to 5 years, it means that even during the summertime it does not melt away entirely, because there are North America, there's northern North America and Russia, Siberia. So it's just surrounded by continental mass, so land masses. So older sea ice in the center of the Arctic may reach 4 meters in thickness, which is not common in the Southern Ocean. While annually formed ice margins are about 1 meter thick. The maximum extent of sea ice is usually reached in spring, the minimum extent in the autumn. Why? I don't know why I wrote this question. चलो बताओ कोई है, मुझे भी सोचना है. So yeah, so why is so sea ice is usually maximum extent is in spring and not in winters. Why? Huh?
That would be the time it would reach its maximum.
Yeah, the lag. Why the lag? Yeah, what's the smile for? No idea? Okay, I'll see. I'll think about why I wrote it. Last time I don't know what I was thinking. So yeah, this.
Can the lag explain like in this way that the most heated day it occurs in around June 21. It should be occurring around June 21 because the sun is at the peak position. But it
For the northern hemisphere.
yeah, but the most warm day in northern hemisphere doesn't occur around that time. It takes a little while, like in July or August. So
why is that?
There also some lag is occurring.
Yeah, why is that?
Not exactly.
So when you say the most like the hottest day on is not on 21st June, you're talking about the northern hemisphere average,
Yes, northern
right? Yeah, yeah.
Because the sun is in the overhead position, so
Right.
we are
So
raising
it
the
takes
maximum.
so it takes and for this similarly for southern ocean it's not on whenever their summer is, right? Peak insolation is, peak solar radiation is.
Similarly, it occurs for winter also.
Right.
The coldest day supposed to be happening in December,
Right.
but it doesn't occur then.
Right.
It is probably occurring in January
So
or
can you?
February.
Yeah, you're right. But why? What could be the reason for that? Why is there a lag in the hottest or position of Earth being closest to the in let's say northern hemisphere, not summer? Yeah.
I don't think the temperature directly correlates with the distance. It barely makes a difference. It's the tilt that
What is it that actually matters in this case?
the tilt.
The tilt. Yes, the tilt. Yes, of course. But what he's saying is like when it's not the distance, it's the tilt. You're right. Seasons. This is what causes seasons. But what he's saying is that peak summer is observed not in not when or hottest day is not when you would expect where sun you have the maximum heat right now tilt, even if it's the tilt. Right now we're getting what is it? What causes the hottest day? And he's trying to correlate it with this question that the maximum ice there's a lag.
This I feel is that post winters only so in winters it would just accumulate more and more till the end of winters where spring starts. So at that point maximum.
Is this question related to like ice is insulating or something like that? So that's why the heat cannot.
How will ice melt in winters? It won't melt in winters. It would just accumulate. So spring starts at maximum.
Right. And why is the minimum then in autumn?
Post summer the minimum. The summers continuously melt. Post summer the autumn minimum. It's just like a CDF, not the PDF.
Yeah. Yeah, and what were you saying?
I was saying that because of like ice insulates the sea from the atmosphere, so that heat cannot like seep into the ice that quickly or escape from the sea that quickly. So that's why there's a lag between the temperature difference, which is between the temperature that's outside and the sea's temperature.
Yeah. Yeah, one of the reasons, yes. And yeah, I think you're correct in saying that, but also there is albedo changes. We have more summer sunlight coming, and that also it gives effect. So that I think a number of factors play into it. Both of you are correct, and what he's saying is also correct in a way that when we say hottest day that is observed, it's not directly correlated by the amount of solar radiation that we're receiving. There's a lot of factors, atmospheric processes and atmospheric constituents, like what do we have, like Delhi is hottest on whatever day, but probably Lucknow is not on that day, even if northern India or Lahore is not maybe the hottest day. So a lot of number of factors are atmospheric factors are in here. So right. So that there is life underwater, and I think this is something that we all know, that there's life underwater in permanently frozen regions where on the poles where sea ice literally like insulates this water, and even though there is minus 30 degrees air, and the temperatures underneath are about 0 degrees, where there is some still some light that lives. So but if it melts, you would have whatever heat that is there in water, that also would escape. This ultimately would change the heat budget that I showed in one of the earlier slides, and again, changing in heat budget would lead to changes in hydrological cycle, and would have again devastating impacts. So what is difference between sea ice and glacial ice? As you can see, yes.
Like at perigee, winter solstice happens, right?
Perigee is near.
Past.
Yeah.
So distance is inversely correlated.
Yes. Yeah.
So it makes sense now that at the point where the tilt would be closest, then summers would maximize. How is distance?
So right now, the way we are, when we are closest to the sun, we have a
winter solstice.
winter season, right?
So that we have winter
Right, so-
solstice on that.
Yeah. Winter solstice. So we have our winter season, but
But our northern hemisphere at that point is just not facing towards.
yes, that's why we have winter season.
Ah.
That is why we have winter season.
So-
Summers have southern hemisphere. We have summers.
So isn't the answer then exactly the tilt? How can anything else not?
Yeah, it is the tilt. Yes, of course. That is what causes seasons.
No.
So if-
About the hottest day and the.
So what I am trying to say is that atmospheric processes also play a big role. Like we are getting the same amount of you're right in saying when we get the maximum amount, but what makes it intense for us to observationally, it is the atmospheric processes. मतलब यहाँ कितना pollution है, right? All that also makes a difference. So we all understand how seasons occur, right? Yeah. So yes, so then there are also mountain glaciers, and you would and also continental ice sheets. These continental ice sheets are basically on continents. Glacier ice, mountain glaciers is because of the altitude. So it's not like we do not have any mountain glaciers around the tropics, because you either need to go northwards or need to go altitude, like higher, right? So in Africa, Kilimanjaro, have you heard of Mount Kilimanjaro? It had mountain glaciers, nice glaciers, Himalayan glaciers. All of them are melting. There is we don't do any of the glacier studies, but glaciologists have continuously reported that the extent of glaciers that were there, they are continuously retreating. So every year they go and find they have inserted a rod, and now it's literally like on the base. So it is kind of retreated. Not in summer season, but it is permanently retreated. Kilimanjaro has effectively no ice now, no glacier now. It's just gone. So I don't know if you've seen this Inconvenient Truth. There's this documentary called An Inconvenient Truth by Al Gore. I sometimes show the trailer. Maybe next class I'll show the trailer. And there in that trailer he shows that Kilimanjaro ice is completely gone. Glaciers on Mount Kilimanjaro because of warming. Do you know who Al Gore was? I'll finish here. But right. So he also received Nobel Prize, Nobel Peace Prize, right, with IPCC.
Nobel Peace Prize.
Nobel Peace Prize, yes. Al Gore received Nobel Peace Prize. I don't remember which. Yeah, but with IPCC, another body which works on climate change. So he was he's been canvassing that climate change is happening, because initially, even now, there are a lot of skeptics which think that climate change is not real, and climate is actually not changing, and we are fine. So he did work a lot in this direction, and because of that he received the Nobel Peace Prize. So probably next time I'll bring that So today I'm going to upload these slides on Moodle. There's only a biosphere component left and a little bit on feedback. So chapter 1 and 2 would essentially be completed by tomorrow, and I'm going to upload it today or tomorrow. Okay.
No attendance policy. No attendance policy नहीं है ना?
Yeah, I'm just thinking what is the best way. I don't want to accumulate so many papers. फिर बाद में बैठ के मैं गिनूं, it's additional work. How do others do? What do the other faculty members do?
Mostly pen paper.
हाँ?
Mostly pen paper.
Pen paper? और बैठ के फिर हिसाब करते हैं? Oh God, I don't.
Can also take on Excel.
मेरा TA
You can do on sheet also. You can count it.
Google Sheet. Oh. कॉपी भी लगा देंगे. कॉपी तो हर बार लगाते हैं सब बच्चे. Okay, I'll see from next time tomorrow.
नहीं बोल रहा है